Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Novia Nurfajrianty. I will present a journal. Title is Energy Absorption from Composite Reinforced with High Performance Auxetic Textile Structure. Introduction. The main issue addressed in the journal is the limited research on the energy absorption capability of composite material reinforced with wet-knit auxetic textile structures with negative Poisson's ratio, particularly those made from high-performance fibers such as para-aramid and hybrid materials. More specifically, the study focused on the following research problems. First, the lack of studies examining how auxetic textile structures can enhance the impact resistance of composite materials, and the absence of direct comparison between the energy absorption performance of auxetic reinforced composite and conventional composites, and the scarcity of experimental data regarding the transfer of negative Poisson's ratio, or NPR, behavior from the auxetic fabric to the resulting composite. This topic is important because energy absorption and impact resistance are critical properties in the development of advanced composite material used for protection, safety, and high-performance application. Traditional composites often fail in brittle modes under impact, whereas auxetic materials, which exhibit a negative Poisson's ratio, show a unique deformation behavior that allows them to absorb and dissipate more impact energy. By combining auxetic textile structure with high-performance fibers such as a para-aramid, the study explores a novel approach to improve the mechanical performance of composite materials under impact conditions. Relevance. First, scientific relevance. Scientifically, this research contributes to understanding of auxetic behavior in textile reinforced composites. Its relevance includes providing experimental evidence on how auxetic geometry influences energy absorption mechanism in composite materials, and demonstrating the transfer of auxetic properties from the knit fabric to the composite structures is a phenomenon rarely explored in previous studies. And for industrial relevance, this research is highly relevant because it supports the development of lightweight, high-stretch, and energy-absorbing materials that can be applied in multiple sectors, such as personal protection, sport industry, aerospace and automotive industries, and for medical application. State-of-the-art of this journal, this research represents a state-of-the-art advancement in the field of auxetic textile reinforced composites, opening new opportunities for developing lightweight, high-impact resistant materials for application in protection, sport, medical device, and aerospace industries. Summary of previous studies. Previous research has widely investigated composite materials reinforced with textile structures to improve impact resistance. However, most studies focus on woven fabric or conventional knit structures or non-auxetic. Research objective. The main objective of the study in the journal are follows. To analyze the impact behavior of composite material reinforced with web knit fabric structures by comparing conventional jersey and auxetic or negative Poisson ratio configuration, and to evaluate the energy absorption capability of auxetic composites produced using high-performance fibers or para-aramid and hybrid materials, para-aramid or polyamide, to experimentally demonstrate that the auxetic property or negative Poisson ratio of the knit fabric can be successfully transferred to the composite after epoxy resin impregnation, and to assess the potential application of auxetic structure composite in field requiring high energy absorption and impact resistance, such as personal protection, sport equipment, defense, and aerospace industry. Overall, this study aimed to develop a new type of composite materials with significantly enhanced energy absorption performance compared to conventional composites, while expanding the practical application of auxetic textiles technology in high-performance engineering materials. Research and methodology. The research flow diagram are material selection, knit fabric production, composite fabrication, Poisson ratio measurements, impact tests, surface and image analysis, data analysis and interpretation, and conclusion. This study used high-performance textile fibers and epoxy resin to fabricate composite material reinforced with both auxetic and conventional knit structures. The following is a detailed description of the material used: reinforcement fibers, para-aramid fibers, polyamide fiber, hybrid fiber composition, and reinforcement fibers, epoxy resin, and hardener. Number 3, supporting materials, flat grid mesh, and gold palladium coating. The physical and mechanical properties can see on table number 1. Right? Composite test, jersey PAR, fiber type 100% para-aramid, fabric structure is conventional, and auxetic PAR, fiber type 100 para-aramid, fabric structure auxetic, and jersey hybrid, fiber type para-aramid plus polyamide, and fabric structure is conventional, and then auxetic hybrid, fiber type para-aramid and polyamide, fabric structure is auxetic. On figure 1, composite produced with epoxy resins, jersey, and auxetic pattern. Equipment used in the study: flat knitting machine to control knitting parameters and to produce web knit fabric, composite preparation tools to impregnate knit fabric with B-resin, epoxy resin, and hardener, curing chamber to ensure complete curing of the epoxy resin, and drop weight impact testing machine to measure the impact response of the composite, scanning electron microscope to analyze the surface morphology, and supporting measurement instrument to ensure precise measurement of thickness, density, and strength formation. And then testing parameter, Poisson's ratio test, drop weight impact test, morphological and damage analysis, And then physical parameters, composite thickness, fiber weight friction, textile temperature, and relative humidity. The figure illustrates the working principle of drop-pick impact test machine, which is used to evaluate the response of a material to impact energy. The concept is simple. An impactor of low mass is dropped from a certain height to strike a specimen, and the system records the force, energy, and the displacement during impact. Instrumented tab. This is the falling object or impactor with a specific mass. The tab is equipped with a load sensor to record the impact force in real time. The tip of the impactor is hemispherical to distribute the impact load evenly on the specimen surface. Data collected from the sensor are used to generate load time and energy time curves. And drop height, the vertical distance between the initial position of the impactor and top surface of the specimen. A higher drop height results in greater potential energy, which is converted to kinetic energy at the moment of impact. And the last sample or test specimen, the material under test, which is the study, is the composite reinforced with auxetic or conventional knit structures. The sample is placed on pictures beneath the impactor. Experimental condition. The experimental conditions are presented in the table below. Knit fabric production conditions and composite fabrication condition. Fabrication method using hand layup method. And the mechanical testing condition using arc impact test using ISO, and impactor mass is 10.044 kilogram. And then morphological analysis condition or using SAM, using Nova nanosam, and for general environmental condition, result and discussion. The result obtaining so that although the auxetic behavior decrease, it is maintained in the produced composite from minus 0.713 in the fabric to minus 0.354 in the composite. In addition, the use of high stiffness filaments such as pararamid in the production of the auxetic wave-knit fabrics resulted in strong improvement of the NPR in the composite when compared to hybrid materials. The representative curves of the composite are shown in Figure 3. As can be seen, single jersey reinforced composites saw a brittle behavior, while the auxetic composites saw a complex behavior with some ductility. The impact behavior shows two different in consequence of the three-dimensional geometry of the composite obtained. This behavior indicates a large ability to absorb energy during impact. It can be also observed in the graphic figure 3 A and B that the contact force increase until the penetration occurs and then decrease until the proportion happens. The average peak load of the auxetic textile composites is lower than jersey composite. Moreover, for the same impact energy, the contact time increased from jersey to auxetic knit fabrics, regardless of the material compositions. Table 4 summarizes the average values, energy absorption, obtained in sample with epoxy resin, and the auxetic para-aramid and hybrid knit reinforced sample absorb total energy of 22.56 and 25.49 respectively, which is much higher higher than the values obtained from the jersey knit fabric of 6.55 and sorry 8 of 8.55 and 6.29 for reason an increase of approximately 2.5 times. For the hybrid knit fabric, this grew from 6.2 to 25.49, represent an increase of 4.1 times. The use of PA yarn in the composition of the hybrid knit fabrics did not influence significantly the result of energy absorption when compared to specimens produced with para-aramid in both type of patterns, considering the mean values and standard deviation obtained. This fact may be important for the use of the hybrid fabric developed as reinforcement in composite materials with low weight along with a lower cost. Figure 5 shows the appearance of the damaged surface of the composite after impact using the nose of the hemispherical impactor. The results show that the maximum impact energy in all tests were high enough to produce total penetration by the impactor in all specimens. It is interesting to note that for the jersey reinforced composites, I for A, B, C, and D, uh, the sample were almost non-deformed to their stiffness, but they were tearing during the impact test. For the auxetic composites, figure as expected, specimens were more deformed than the jersey composites. This can be justified due to the 3D configuration of the sample that allows a larger structural deformation of a composite. For the para-aramid composite, regardless of the wave knit structure, the tear dimension was greater than in the hybrid composite. The image saw as favored direction of failure, indicating an elongation in the front and rear side. According to the literature, elongated failures flowing in the fiber directions are associated with the fiber matrix interface rupture and subsequent delamination. In this study, doesn't occur delamination, but probably the use of the para-aramid yarn increased the influence of the rupture of the fiber matrix. This morphological characteristic agrees that the influence of the rupture of the interface to the failure or a composite under impact arise from the middle surface to the tension side of the composite to the rear surface. For the hybrid composite, the front and rear side have a rounded dome aspect, indicating a more homogeneous deformation. And this is failure type is an indicative of metric crashing. Several failure mechanisms can appear in the composite materials. Some photographs of all the infected specimens are shown in figure 6 and 7. It is evident by the specimen that a combination of matrix cracking and fiber breakage is the predominant failure models. In the figures, A and B represent A and B represent the composite before the impact test. For the jersey composite, after the impact test, with a 90 magnification, figure B and 7B indicate fiber breakage. With a 500 magnification, figure C, it can be seen that there are vacant space. These areas can indicate matrix debonding at the plane level and can lead to localized strain. However, with this same magnification for the auxetic composite, it is not possible to observe the space mentioned before. In auxetic composite, it is also possible to observe the crack in the matrix. For figure E, however, with 500 magnification for the auxetic composite, it is not possible to observe dense vacant space being shown before. The situation forwards with the graphs presented in figure 3, which show that compositor impacts like cyclic credit present a rotatory behavior during the impact test. Unlike what occurs with compositor imports by just fabrics, that present a more fragile behavior, justifying the matrix debonding as shown in the same photographs. Therefore, image of oxidative composite, para-Arabic, and hybrid, not some matrix debonding. In this way, the composite reinforced by the auxetic structures also provide a better structural introductory of composite after impact. Main interpretation of journalism. The main interpretation of this study focused on how auxetic net fabric structures with a negative piezospatial influence the energy absorption capacity, impact behavior, and structural integrity of high-performance fiber reinforced composite materials. The key point of interpretation are as follows. Auxetic structures significantly enhance energy absorption. The composite reinforced with auxetic fabrics were able to absorb impact energy 2.5 to 4 times higher than composite with conventional disease structures. This indicates that the effect of the structure's geometry driven has a highly significant influence on the mechanical properties of composites, even more dominant than the type of fiber used. The mechanism behind this improvement is due to the lateral deformation characteristic of auxetic materials, where the material expands laterally under tension, creating denser areas to absorb impact energy. And auxetic structures alter impact behavior from brittle to ductile. Conventional composite exhibit brittle failure with rapid fracture after reaching liquid load. In contrast, auxetic composites show two-fold peak or double peak on the rectangle indicating gradual deformation and more uniform distribution of impact energy. This phenomenon suggests that the auxetic structure helps delay damage and allows the composites to withstand much longer before failure. And auxetic structures improve force impact structural integrity. Some observations show that jersey composite experience metric cracking and fiber leakage, whereas auxetic composite display a more intact surface without significant lamination. This means the 3D auxetic structures helps dampen and distribute impact stresses, reducing micro-damage around the impact zone. As a result, auxetic composites are more resistant to repeated failure and structurally more stable after impact. Auxetic effects are more significant than fiber type. Both pure para-aramid fiber and hybrid fiber saw similar performance improvements when combined with auxetic structures. Even the hybrid fiber had lower stiffness, the geometric effect of the auxetic structure still provide high energy absorption. This demonstrates that textile structure design is equally important or even more important than fiber selection in the development of high-performance composites. And then, broad potential application in industry with a combination of lightweight, strength, and high energy absorption capability, auxetic composites have good potential for application in personal protection, sport industry, defense, and aerospace, and for medical applications. Overall, the result of the study confirmed that auxetic geometry designed to with knitting techniques directly enhance composite performance under impact via mechanism of higher energy absorption, more controlled deformation, and minimal damage. Therefore, this research provides important scientific and practical contribution showing that textile structure design can be used as an engineering strategy to create smart, adapted composite materials with superior energy absorption capabilities. The relationship of research result with previous theory or literature. This study not only produced new experimental findings but also reinforced and extended previous theories regarding auxetic materials and textile reinforced composite. The relationship between the result of this study and the underlying literature is as follows. Relation to fundamental auxetic material theory, support for previous research on textile composites, consistency with previous auxetic research on 3D composite, novel contribution to the literature, implication for material design theory. Most important are innovative findings. The study presents several key innovative findings that contribute directly to the advancement of composite materials and technical textile. The most important and original points are as follows. Auxetic structure successfully transferred from fabric to composite. The innovation is actual transfer of auxetic properties into solid composite material, not just a theoretical concept. Auxetic structures significantly enhance energy absorption, and the innovation is demonstrate that geometry-driven design can drastically improve composite mechanical performance without changing the base material and change in Mechanical behavior from detail to ductile. The innovation is control of composite failure mechanism to textile structure design, not just material modification, and structural effect dominate over fiber type. The innovation is efficiency-driven approach, high performance achieved with more economical materials through smart structural design, and new scientific contribution in textile structure composite. The innovation is first application of auxetic concept in high performance web knit composite system and great potential in industrial application. The innovation is opens opportunities for applying auxetic composite in protective and energy dissipating structures. Auxetic knit fabric structure based on high-performance fibers can transfer negative Poisson's speed ratio behavior into solid composite materials, resulting in remarkable improvement in energy absorption capacity and impact resistance. Thus, this research marks a foundational step in the development of auxetic textile composites that are not only strong but also adaptive to improve energy, representing a significant move toward the next generation of smart materials in engineering and protective industry. Conclusion. Summary of main result. Auxetic behavior retained after recent Indonesia. Para-aramid fiber yield higher NPR and energy absorption. Auxetic structure absorb to war more impact energy and will not change from brittle to ductile and then high application potential. This study demonstrates that para-aramid-based auxetic knit fabrics can successfully transfer the negative Poisson spatial behavior to epoxy composites, resulting in a significant improvement in impact energy absorption and damage resistance. The combination of auxetic geometry and high-performance fibers offers a promising route for the development of lightweight, high-energy absorbing materials for protective and advanced structural application. Implication. The type of implication are scientific, technological, practical, design innovation, and for scientific, demonstrate that auxetic properties can be transferred from fluid fabric to composite, reinforcing the structure properties performance relationship, and for technological, this provide a reliable experimental foundation for future numerical modeling and simulation-based design of auxetic composite. Uh, and practical offers a new pathway for developing lightweight, energy-absorbing materials for protective, automotive, and aerospace application. And for design innovation, promotes geometry-driven material design as a strategy for next-generation smart composite materials. Scientifically, this research deepened the understanding of how auxetic geometries influence the mechanical performance of composite materials, while practically it opens new opportunities for lightweight, high-energy absorbing materials in protective systems, transportation, and advanced structural application. Unique contribution of the study. This study uniquely demonstrates that a para-aramid-based wave-knit auxetic fabric can transfer its negative Poisson ratio behavior to an epoxy composite, resulting in significant enhancement in impact energy absorption and improving the visibility of auxetic structures for lightweight, high-performance protective materials. And methodological limitation of the study uh, for aspect modeling, no numerical or finite element analysis used, experimental scope, small sample size, and limited structural variation. And for impact testing is only single drop test performance. And for microstructural analysis is insufficient detail on recent fiber interaction. And for mechanical evaluation is the tensile or flexural tests conducted. And for thermal aspect is no assessment of temperature effect during impact. And future research recommendation are focus numerical modeling is to understand stress strain behavior and validate experiment, auxetic geometry variation to identify the most efficient auxetic structures, and for connecting and resin parameters to optimize structures, metrics, interaction, and performance, and to comprehensive mechanical testing to evaluate strength, toughness, and durability, thermomechanical and environmental testing to assess long-term stability and performance, and for new materials and fabrication method to develop sustainable high-performance composites, and for industrial application optimization to enable practical use in protection and lightweight structure. Future research should combine numerical simulation and experimental method, explore diverse auxetic geometries and material systems, and perform comprehensive mechanical and environmental testing to gain a holistic understanding of auxetic composite behavior. Emphasis on material innovation and industrial implementation will accelerate the development of lightweight, high-energy absorbing material for protective and structural engineering applications. It's enough for me. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.